So, what is up? Good morning, good afternoon, or good evening, depending on where you are. And when you're watching this presentation, we're in the group number three. My name is Kyle, and our main goal with this humble work is to explain what real time PCR really is, the whole methodology behind this process, and the applications existed in the medical field. We want to thank our great professor, Dr. Igor Nasser, for this opportunity, and we're honored to be assigned with this challenge. I would say because it's been a little bit of a headache. I'll be honest, to study the whole thing and trying to understand with the little that I know, understanding this complex process, but we've come to the sense that this whole thing is really important. The process is in fact revolutionary, and it's been helping our society greatly. And right now, as y'all will watch, as we go in this presentation, as we go on and deeper about real-time PCR, y'all will realize how important the thing is and how this thing has been ameliorating others people's lives and the great impact that it had in the medical field and still has. It is a gold standard test for many diseases, and it's greatly used here in Brazil and around the world. And this presentation is being performed in English because we believe we can take our medical program to another level. So there's nothing better than speaking the language that the whole world does. So that's why it's in English. I'm sorry for the people that cannot understand me. Maybe next time I can do it in Portuguese or not. We're just gonna keep doing it in English. But I want to thank you all for listening to me. I hope y'all can understand the whole thing. And let's go. Let's start it. So the first question that we have is what is PCR? PCR or PCR is short for polymerase chain reaction, and it is a technique, a molecular test invented by Kerry Mullis in 1983. What he wanted to do is he wanted to use a primer to produce many copies of a DNA strand. So, what Kerry Mullis invented, the process behind PCR works like this. You will need a DNA sample, you will collect a DNA sample, and you will put it in a high temperature, usually 95 degrees Celsius. And then, while after you do that, naturally the DNA is gonna denaturate. So, y'all know that a DNA is a double helix, is a double stranded. So, when we heat it up, naturally, because of the proteins in it, in the nucleotides, it will unbind. It will unbind. It's not very, our DNA is not very resistant to high temperatures, as y'all know. So it will unbind, and when it's unbinded, they let it cool down. So while it's cooling down, they will use a primer that will recognize specific regions in the DNA. And after that being done, they will use DNA polymerase to seal this new double stranded DNA copy. So if we had only one copy of DNA, after the whole process of PCR, we're gonna have the double of DNA copies as we had before. When we do this whole process of denaturating, annealing, that is using the primer, and then extending the DNA copy, sealing it with the DNA polymerase, we call it a cycle. That's a PCR cycle. Okay, but back then when Kerry Mullis did it, he had a problem. So the PCR process was very hard to be accomplished, to be finished, because our natural DNA polymerase doesn't it's not resistant to high temperatures, as we know. So another guy, a scientist named Randall Psyche, in 1988, discovered a bacteria called Thermus aquaticus, and this bacteria lives in hot springs. So its DNA polymerase is very resistant to high temperatures. It is called Taq polymerase. So he discovered this thing, and they started using Taq polymerase in the PCR process, allowing the thing to be faster and to be more efficient, because it would take forever and it will fail many times because the DNA polymerase wouldn't resist to the high temperatures. And sometimes it's 95 degrees. There's no way our DNA polymerase can resist to that. So, with that, the PCR was invented and it started being largely and widely done around the world. And we could see that during the COVID pandemic that we had in 2019, 2020. And we could see that because uh, we would run a lot of PCR tests to see if people actually had COVID and in what phase of COVID people were. As you can see right there in the image, they used the swabs, and I myself, I had a swab almost poking my brains out. It was very uncomfortable, but it gave me the diagnosis of COVID-19, and it was really important because I had actually a very fast diagnosis in almost like couple hours or like a couple minutes, because the whole thing is very fast and it works superbly. It's amazing. So after that being said, um, after we explained PCR, the next question is, what is real-time PCR? Real-time PCR is also known as quantitative PCR or qPCR. It is a variation of PCR, a branch of the regular PCR process that allows the amplification, that is a process in the regular PCR, of uh, specific regions of DNA studied, and also allows the detection of fragments wanted. And by the way, I'm talking about a pathogens material that is used in the medical field a lot. And it allows the two things, the amplification and the detection of the fragments, to happen at the same time. And it also provides a greater precision of this of the quantitation. By already mentioning the quantitation step, I want to point out that in order for the step to happen, the use of fluorescent DNA markers, dyes, in general, dyes, is greatly needed. So we're going to see the first example here of a fluorescent marker used in this kind of test. The first one and the most common one, because it's cheaper, you're going to see that. I'm going to talk about that, is the cyber green. So, cyber green is a free floating fluorescent dye that binds to double stranded DNA, increasing its fluorescence according to the presence of the targeted gene that will bond with the dye. As you can see right there, we're gonna do the natural PCR process, denaturation. Then we're gonna use the primer, like I said, and then DNA polymerases comes in, seals the thing, and when this marker detects a double-stranded DNA gene that we specifically marked for, it will bind itself to it and it will glow. And because this thing glows and it marks specific regions that we want to study, we can see if there is a great concentration of the gene of this pathogen. Of course, we're talking about viruses and bacteria here. We're talking about medical tests. So we can see the concentration of this marker, and consequently, we can see the concentration of this specific gene. That's crazy. Actually, that's crazy. That's new stuff. That's revolutionary, like I said in the beginning of the presentation. And cyber green has its ups and downs. By the way, the fluorescence that I was talking about, the cyber green provides, is caught by an equipment called applied biosystems that will tell if the expression of the gene is high or low. Like I said, if there's a great concentration, consequently we're gonna have a great glow. Like I said, the thing is gonna glow for real, and these in this applied biosystems is gonna catch that. Okay. Oh, like I was saying, the cyber green has its ups and downs. So one up is that cyber green is cheaper. It is a cheaper method of doing a qPCR, quantitative PCR. But on the other hand, it cannot target more than one gene in a single analysis, and it also fails more often, even though the fail rate for this kind of procedure is ridiculously low. So there is another technique, and this technique is newer. I would say it is very fancy, very elegant, like our Dr. Igor Nasser says. It's very elegant, and it uses a probe called TechMan, as I'm showing you right now in the slide. So TechMan is a reaction method that will use two primers and the probe, like I said, the on segment. And this probe has in its composition two ends. One end holds the fluorescent dye, and the other end holds a quencher. And this quencher impedes the dye to produce light. So in the beginning of the process, you're gonna do the denaturating. You're gonna use the primers, and together with the primers, you're gonna have a probe that will attach itself to a single-stranded DNA, a DNA chain, a chain cord. It will attach itself to it, and when the DNA polymerases does its job, it will cut those heads and separate them. When both heads are separated, the dye and the quencher are separated, the dye is allowed to glow. It will glow because the quencher was the thing that was impeding the dye from glowing. So when we have a great multiplication of this particular gene that we are studying, the DNA of a pathogen present in the mixture in the sample that we're studying. Both heads are cut by the DNA polymerase, and it glows again. So we're going to use the same machine as we used in cyber green, that is the applied systems, to see if it is a um, if it is glowing a lot or just a little. So we're going to see the actual concentration of this gene in the mixture, in the sample that we are analyzing right now. So, but it also, TechMan also has its ups and downs. It is, it's not so cheap like Cyber Green, but its ups is that TechMan um, is more specific, and you can target more than a gene in a single analysis. You can target more. So, and it just makes the whole thing more efficient than Cyber Green. But to understand this, we have to learn how to interpret a graph, a PCR graph. And a PCR graph shows the graph shows the increasing of the fluorescence of this gene that I'm targeting as we run cycles. And one thing that is important for you to understand is the sooner the peak of this specific gene shows up in the graph, the more concentrated this gene is in a DNA sample, in the mixture that we used in the beginning. So if I have gene number 1 peaking at cycle number 9, for example, at the ninth cycle, and gene number 2 peaking at the 12th cycle, cycle number 12, I have to understand that gene number 1 is more abundant because it took less cycles to peak. But what kind of peak is that, and when do I see that the concentration is actually relevant for my study, for my research? So there are a couple things that you need to look at the graph and recognize. So right there, as you can see in the graph, we have a CT line, or a CT point. And CT stands for cycle threshold. And this cycle threshold is a measure of how much DNA is in the sample. It shows you once your graph, that is, by the way, in exponential growth. Like I said in the beginning of the presentation, there will be a time where your DNA, your concentration of DNA will start doubling, and that's the exponential growth phase. And it shows when in this phase that I just mentioned, that you have a relevant amount of DNA present in your sample. So it will be the line that will tell you that you actually have a decent amount of genes, of gene concentration of the gene that you're looking for. And that's the CT line. Eventually, your concentration will reach a plateau, will reach a peak, and will fade away. Because as you go on and you do cycles, lots and lots of cycles, it stops growing in an exponential rate. And like I said, one important thing to know is that um, when your gene, it shows up very early, I'm talking about the number of cycles here, And when it shows up very early, that means that there is a significant concentration of this gene in the sample. And when we're looking at viruses and bacteria, that means that that person is infected with the gene that you're looking for, the gene that you were studying, that you're targeting. All right. The You got to understand that the whole curve showed in the graph shows the fluorescence, as you can read right there, and the number of cycles. Okay. The application of this test in the medical fields is that, first one, we can have a very fast diagnosis because it takes only a couple hours for the diagnosis to come out, like we saw in the pandemic, the COVID pandemic. And it helped a lot because we could have a really fast diagnosis, and the faster your diagnosis is, the faster you get your treatment. You have to understand that. And it also helps a lot of people that carry HIV or AIDS, because these people have to keep track of their viral load in order to do stuff or not do stuff, how much of their prep they're going to take, and this kind of things. They have to hold accountable. They have to know how much of the viral load is in them. And one thing that I actually forgot to mention is that um, you can tell, not exactly though, but you can tell how much of a virus is present, not in numbers again, but you can tell how much of the virus is present in someone's organism by running the PCR. So if you're running a PCR in a person that has HIV, is an HIV carrier, and that person has a very low peak, I would say, that means that the viral load is low. And with the PCR, you can also tell, like we saw in the pandemic, you can see if the person is infectious or not, if the person will infect other people or not, because of the viral load. You can look at the graph and tell if the person needs to stay away from people, cannot have contact with other people because will infect other people or not. So that's the importance of the PCR. And you can also, with PCR, study genetic material. You can study the molecules. You can study new viruses, and you can study the different kinds of viruses and mutations that happen. That's how important PCR is. And like I said, we used a lot of PCR during the COVID pandemic. It was largely used, and it was very useful for all of us. Thanks to PCR, we could diagnose people. We saved a lot of lives with the through the use of PCR. And again, they will use a nose swab, like you're seeing the lady right there sticking the nose swab in that dude's nose right there, and collect the DNA sample and just run the test and run the test. I did one myself at the hospital and diagnosed me with COVID. It was a very important diagnosis because the doctor was he was unsure of what I had. He thought I had a general infection, but I actually had COVID. Thanks to God. But yeah, that's how important it is. So, to in conclusion, we can say that real-time PCR is a revolutionary process because it gives us fast diagnosis. We can study viruses, we can study bacteria, we can save people's lives. It also allows you to have a more effective treatment because it will be very specific about the outcomes in a test. It will be very specific about the kind of infection that you have, the kind of pathogens, genes that you got inside your DNA. And it provides a safer lifestyle for HIV carriers because they can keep track of their viral load and they can live better because they're not always worried about their what's gonna happen or how much of the virus I got inside of me, if it's if it's getting dangerous and this kind of stuff. They can keep track of that. So that's how important real-time PCR is. I've talked about the different applications of real-time PCR, and I hope y'all enjoyed it, understood it. I'm sorry about my English. I'm very rusty. It's been a while since I've been in the States. So I want to thank again Dr. Igor Nase for this opportunity, this unique opportunity. And me and my group, we want to especially thank God for his beautiful creation that amazes us with so much complexity and perfection. Um, Thank you very much for listening to me, and I hope I see y'all next semester. And that's it. Thank you.